Hey, it's Gal, and in this video, I'm going to show you how to perform acid catalyzed hydration of an alkene. So let's talk a little bit about its name first. This guy over here is an alkene. And so we are hydrating this alkene with water, hence the hydration of an alkene. And what about acid catalyzed? Where does that come from? That comes from the fact that we are using H2SO4, also known as hydrosulfuric acid. And so hydrosulfuric acid is catalyzing this reaction. Catalysts are usually drawn above the arrow. And so this acid is catalyzing the reaction, hence the name acid catalyzed hydration of an alkene. Now, there's a few steps to this mechanism. But first, what I want you to know is that H2O and H2SO4 are actually going to react with one another. So let's take a look to see how that happens. So if we zoom in here, we see that water is going to take a hydrogen from H2SO4 and become H3O+. So we see how water gained a hydrogen. H2SO4 is going to lose a hydrogen and become HSO4-. And real quick here, I just want to show you what that looks like in the form of a mechanism. And so this guy over here is hydrosulfuric acid. And he looks a little scary, but all he is H2SO4. And so water is going to say, hey, hydrosulfuric acid, I really like that hydrogen of yours. I think I'm going to take it. And hydrosulfuric acid says, sure, but you got to give me some electron density in return. And so we draw an arrow going from the lone pair on the oxygen atom to the hydrogen, and from the bond between the hydrogen and oxygen to the oxygen. And so it's a fair exchange because what happens is this arrow shows the flow of electron density. So now water took that extra hydrogen over here and it lost its lone pair. So now it only has one lone pair. And where did that lone pair go? It actually traveled onto the hydrosulfuric acid. So while hydrosulfuric acid only had 2 lone pairs on this oxygen before, now it has 3 lone pairs. And so we see that it's a fair exchange. Water received a hydrogen and H2SO4 received a lone pair. So as for the charges, we can real quickly calculate formal charge, where formal charge is equal to valence electrons minus surrounding electrons. And oxygen here has 6 valence electrons, and surrounding it right now is 1, 2, 3, 4, 5, 6, and 1 from the bond, which makes 7 surrounding electrons, which makes for a total charge of -1. And so we see that over here it has a negative charge. If we calculate the formal charge for this oxygen atom, it's going to be equal to valence electrons minus surrounding electrons. And as we know, oxygen has 6 valence electrons, and surrounding it right now is 1, 2, and 1 from each bond, which makes for a total of 5 surrounding electrons. So we have a total charge here of +1. Now, you don't necessarily need to know this. I'm just showing it to you once so you can see where H3O+ comes from, because that's what we're going to be working with in this mechanism. So now let's go ahead and erase all of this. So here we have H3O+. And whenever you do a mechanism, at each step you want to label who's going to act as a nucleophile and who's going to act as an electrophile. And if you recall from our previous video, positively charged things, especially acids, like to act as electrophiles. So here our hydronium is going to act as an electrophile. And that's right, I called it hydronium. Hydronium is the name for H3O+. And whenever something ends in -ium, it usually means that it has a positive charge. So we know that positively charged things like to act as electrophiles, and therefore hydronium is going to act as our electrophile. And therefore, our alkene is going to be our nucleophile. So we know that the arrow always goes from nucleophile to electrophile. So what's going to happen here is this alkene is going to say, hey, hydronium, I really like your hydrogen atom. I think I want to take it. And hydronium says, sure, just give me a lone pair in return. So now what we do is we draw the arrow going from the double bond to the hydrogen, and from between the hydrogen and oxygen onto the oxygen to show that that bond is going to break. So now we've broken up that bond on the alkene and we've turned it into an alkane. And what's going to happen is this hydrogen is either going to go on to this carbon or this carbon because that's where the double bond broke. Now to understand the next part of this problem, I'm going to draw in the hydrogen that was originally on this structure, right over here. And so now I want to show you what's going to happen if we add this hydrogen. If we add this hydrogen onto this carbon, we know that this carbon is going to have 4 bonds and be happy, but this carbon is only going to have 3, and so it's going to bear the positive charge. However, if we throw the hydrogen atom onto this carbon, then this carbon is going to be happy and have 4 bonds, but this carbon is only going to have 3, and it's going to bear the positive charge. Remember that a carbon bonded to 3 things has a positive charge. So now my question to you is, would we rather have the positive charge on this carbon or on this carbon? And the answer is, we would rather have the positive charge on this carbon because that's going to give us a tertiary stabilized carbocation. And so, if you recall, the order goes from primary to secondary to tertiary, with tertiary being the most stable carbocation. So let's say we put the carbocation on this carbon. This would only be secondary because this carbon atom's only attached to 2 alkyl groups. Remember, we don't count the hydrogen there. While putting the carbocation on this carbon is going to give us a tertiary carbocation because it's going to be attached to 3 alkyl groups. Therefore, that's going to be a more stable intermediate. So now what happens is hydronium lost its hydrogen. So it was once H3O plus, but now it's going to be H2O. And so it once had only 1 lone pair, but because it gave up its hydrogen, in exchange for that, it received another lone pair. So now it has 2. And it makes sense because the oxygen and water should have 2 lone pairs. So if we wanted to calculate the formal charge for this oxygen atom, it's going to be equal to valence electrons minus surrounding electrons. Oxygen has 6 valence electrons, and surrounding it right now is 1, 2, 3, 4, and 1 from each bond, which makes for a total of 6 surrounding electrons. 6 minus 6 is 0. And therefore, this oxygen has a formal charge of 0. And here we formed a carbocation intermediate, which just means that the carbon here has a positive charge on it. Cation means positive charge and carbo means carbon. So we have a positively charged carbon right over here. And so they might ask you a multiple choice question about that, like what's the intermediate for acid catalyzed hydration of an alkene? And you could say it's a carbocation intermediate. So now we're at the second step of our reaction, and we gotta relabel who's gonna be our nucleophile and who's gonna be our electrophile. Remember we said that positively charged species like to act as electrophiles. And water here is actually an amphoteric species. And what that means is water can act as both a nucleophile or an electrophile, depending on what it's with. So because water here is with an electrophile, it's going to act as a nucleophile. Remember that the nucleophile does the attacking. And so we're going to draw an arrow going from the lone pair on the oxygen over to that carbocation carbon. And the reason why is because this carbon here is missing a bond, it only has 3 bonds right now. So it would love to form a new bond with this oxygen molecule. So the oxygen says, sure, I'm going to use my lone pair to create a bond between us. And so that's going to look something like this. Now we know that there's a hydrogen atom here, but we don't need to draw it in. We see here that this oxygen lost a lone pair, so where it initially had 2 lone pairs, now it only has 1 because it used that other one to form the bond between it and carbon. So now what's the charge going to be on this oxygen atom? If we go ahead and recalculate formal charge for that oxygen atom, it's going to be equal to valence electrons minus surrounding electrons. Oxygen has 6 valence electrons, and surrounding it right now is 1 from each bond and 2 from that lone pair, which makes for a total of 5 surrounding electrons. 6 minus 5 gives a positive charge of 1. And so this oxygen atom here has a positive 1 charge. And so you might recall in the beginning of the video that H2O and H2SO4 combined to form H3O+. And what happened to H2SO4 when it gave away that hydrogen? What did it become? It became HSO4 minus. So I'm going to go ahead and draw that in over here. And so here I have redrawn for you HSO4 minus. And it's going to come back and reclaim its hydrogen. So this oxygen here is going to say, hey, give me back this hydrogen over here. And it's going to throw those electrons onto the oxygen. And so now what we formed is this alkane with an alcohol group attached to it. And as a byproduct, HSO4 minus regained its hydrogen to become H2SO4. And so what's really cool here is you might have learned in chemistry that catalysts are never used up in the reaction. And that might be ringing some bells in your ears. And now you can see why. This catalyst here was used in the beginning of the reaction to protonate the water and get the reaction going. So it lost one of its hydrogens by protonating that water and forming the H3O+. But in the end, it came back to retrieve its hydrogen as HSO4 minus. So as HSO4 minus gained back its hydrogen, it became H2SO4 again. And so we see here that the catalyst was regenerated. So now you understand why the catalyst is not used up in the reaction. And I think that's kind of cool. Now, you're not always going to need to perform the mechanism on your test. Your teacher might just show you these reagents and ask you, what's the product going to be? And so a really easy shortcut you can just take is to break your double bond and make it a single bond and throw the alcohol group onto the more substituted carbon. So if we erase this hydrogen atom here, we see that all we need to do is break this double bond and throw the alcohol group onto the more substituted carbon of the double bond. So this carbon is going to be more substituted because it has more alkyl carbon groups. So we're going to throw the alcohol group over here. And that's going to form something called our Markovnikov product. And that just means that the alcohol group is forming on that more substituted carbon. And that's because if we look back to our intermediate here, it was more stable with the carbocation being on the more substituted carbon. And that's where the water molecule joined. So because it gives rise to a more stable intermediate, the product is going to be Markovnikov in the sense that that alcohol group is going to be put onto that more substituted carbon. Now that you know this shortcut, let's go ahead and try some example problems. And so here I have a few examples laid out for you. Let's do the first one together and then you can try the rest on your own. So remember I told you that whenever you see H2O and H2SO4, I want you to automatically think of H3O+, since that's what we're going to be working with. But we don't need to remember the mechanism or anything crazy like that. All we need to know is that whenever we have an alkene being added to water and hydrosulfuric acid, the double bond is going to break here. So we are going to form an alkane. And so our double bond has broken. Then we need to remember that an alcohol group is going to attach to one of the two carbons that once had the double bond. And so these two carbons here are the same, so it doesn't matter which carbon we put the alcohol group on. So I'll just put it here on the right. Now, this molecule here has a chiral center. And if you recall from our previous videos, a chiral center is any atom that's attached to 4 different groups. Can you take a moment to tell me where the chiral center is for this structure? So the chiral center is right over here. There's this hydrogen that we haven't drawn in here. And so we see that this atom is chiral because it's attached to 4 different groups: a hydrogen, a methyl, an ethyl, and an alcohol. And why do we care about that? It's because chiral centers have rotations about their chiral atoms. So we know that this chiral atom is going to be rotating either this way or this way. And so that means that we can actually form 2 different products. So what your professor will want you to do is draw the product twice. And once it will be on a wedge, and the second time it'll be on a dash. And these are 2 different products because these 2 guys are actually enantiomers of each other. And you might recall enantiomers from our previous video. So one of these guys is going to be R and the other one is going to be S, meaning they have different rotations about their chiral atoms. If you're a bit fuzzy on this, feel free to check out my enantiomer video that I've linked down below. And so now that you know that, it's imperative that we write both products down because both are equally likely to form. And why is that? It's because we have an intermediate of a carbocation. So you know that our intermediate would have looked like this. And so this guy over here is a carbocation intermediate. And so whenever you have a carbocation intermediate, that leads you to having racemic products. And all that racemic products means is that you're going to form both enantiomers, or R and S. And that's because if we take a look at our carbocation intermediate, this carbon over here is going to be missing a bond. So when the water group is going to come and attack, it can either come from the front and form this structure, or it can come from the back and form this structure. So we say that there is no stereoselectivity. Carbocations are not stereoselective, and so they're good at forming both products. So if you come across a problem like this on your exam, and you form a product that has chirality, you will have to draw both products to show that this is a racemic reaction and that both products are likely to form. Now go ahead and try the next one on your own. So for example number 2, we know that when adding H2O and H2SO4, we're technically adding H3O plus to this alkene. And so what's going to happen is this double bond here is going to break. So we know that we're going to have an alkane as our answer. And so we're going to form the alcohol group either on this carbon or on this carbon. Now which carbon is it going to form on? It's going to form on this carbon because this carbon has more substituted. And so it would form a more stable carbocation intermediate over here rather than over here. So we know that our carbocation intermediate is going to be more stable secondary-wise, and that our alcohol group is going to join to that carbon. Now we got to ask ourselves the big question. Is this a chiral molecule? Are there any chiral centers here? And the answer is yes. We have a chiral center right over here. And that's because there's a hydrogen we haven't drawn in. So we see that this atom over here is chiral because it's attached to a hydrogen, an alcohol, a propyl group, and a methyl group. Because this molecule is chiral, we're going to have to show that both products are going to form, as in the wedged position and as in the dashed position. So again, we're showing that this is a racemic mixture by drawing both enantiomers. Now, for the last one here, it's the same situation. All we need to know is that this double bond over here is going to break, and we're either going to add an alcohol group to this carbon or this carbon. So you tell me, where's the alcohol group going to go? It's going to go to the bottom carbon because that is more substituted. Remember, we're adding it to the more substituted carbon because that's what allows us to form the Markovnikov product. If in some strange situation the alcohol group went to the less substituted carbon, as in this one, then that would form the anti-Markovnikov product. So we know that the intermediate for this guy is going to look like this. And that's because the carbocation is going to be on that more substituted carbon because that's where it's most stable. Remember, the order of stability goes primary to secondary to tertiary. So when this water group comes in, it's going to come and attack that more substituted carbon carbocation. And that's why our product is going to have the alcohol group attaching to the more substituted carbon of that double bond, hence forming our Markovnikov product. We're going to add the alcohol group to the more substituted carbon over here. And now we got to ask ourselves a big question. Is this a chiral molecule? And the answer is no. That's because there's a plane of symmetry going down this molecule. And so we see here that this carbon atom is not attached to 4 different groups. It's attached to a methyl, an alcohol group, and these two guys are exactly the same. Therefore, it's not attached to 4 different groups, and it is not chiral. So this molecule here is not chiral. So because it lacks chirality, we're only going to form its one product. So you can either leave your answer choice like this, but let's say you were to draw it both on a wedge and a dash. So we might put this alcohol group on a wedge and this alcohol group on a dash. So our methyl groups, right, it can't be in the plane of the page. We got to also put them on the opposite group. And so now you might have thought that you drew 2 different products, but joke's on you because these guys are actually the same. So the reason why is because there's a plane of symmetry along this molecule. So let's say you were to turn the structure around its axis. What would happen is the groups that were once pointing towards you are now going to be pointing into the page. And so the groups that were pointing into the page are now going to be pointing towards you when you rotate it. And again, this is the hardest part of organic chemistry, is trying to see how these guys are the same and rotating it in your head. So if you're having trouble on this, try working with a molecular kit so you can see that visual rotation in person. So because these 2 guys are the same, we only need to draw one of them. So we could just erase this guy over here, since he's exactly the same as this one. And so we only have one product for this problem. Now, there's a shortcut to this. Let's say you got tired, or maybe you were on your test and you didn't have a lot of time. Instead of drawing both enantiomers, what you can do is just draw one of the enantiomers and then write plus enantiomer, EN for short. You can even do that for number 2. So you can erase the enantiomer and just write plus enantiomer. And so this is going to indicate that both your answer choices will form. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!